Whoa, still big. There we go. So lecture 3.3, graphs to state space. Part 1, normal trees. Before we introduce the algorithm for constructing the state space model in lecture 3.4, we introduced the first step from the system graph to the state space model called the normal tree. It is a subgraph of the system's linear graph. So you draw the system graph, and then there's a subset of that that's going to be called the normal tree. Okay, that's what this lecture is about. And we're gonna do some editing on the fly here. It's gonna be really fun. Okay, so you gotta be ready for this. So in the fall, oh geez, my trackpad's not working. Okay. Oh, look at this though. I'm fast at it now. I just go bang, and then bang, and I'm not back, and I'm back. Okay, sweet. So in the following, we will consider a connected graph with, so instead of B branches, we're gonna call it E edges. Okay. Otherwise, the names sort of step on each other, of which S are sources. There are 2 E minus S unknown across and through variables. So that's how many equations we need. We have E minus S elemental equations, and for the rest we will write continuity and compatibility equations. N is the number of nodes, and the following rules must be respected as we do the construction. So we're going to get a list of priorities in terms of what to include in the normal tree, but as we select them in this level of priority, we always need to respect these 2 rules. Okay? So rule 1, there can be no loops. So our graphs have lots of loops, so we can't when we select a normal tree from it, we can't create any loops. And rule 2, every node must be connected. So you got to reach every node with a normal tree, but you can't create any loops. Okay. So form a normal tree with the following steps. For an inline example, we will construct a normal tree from the linear graph for an electronic system shown at right. So this is our a linear graph for a simple electronic system that's got 2 resistors, a capacitor, an inductor, and a voltage source. Okay? So we'll use this as we go to illustrate each of these steps. So the first step is to include all nodes. Now I'm going to use just black on this because it's already grayed out, so I can just draw on top of it in black. But if you already drew in like black pen or whatnot, you can use another color to highlight the original graph. I find that either highlighting it or drawing another color to show where the normal tree is on the linear graph is the best way to go. Instead of redrawing it separately, it's a little bit harder to see how the normal tree connects to the rest of the graph if you draw it separately. So, great. So include all across variable sources. So we still have all our nodes, right? So we got to copy that down. And we have to look for all of our across variable sources. Do we have any in this example? Yeah, this voltage source is an across variable source, right? Voltage for electronic systems being the across variable. So this is included now in the normal tree. And at each step, we like to stop and evaluate whether or not we're done, okay? Because we're just going in this level of priority. But once we've reached the end of our possible selections of edges to come into our normal tree, we can stop there. So how do we know if we're done or not at this point? So we know that we have to connect every node, right? So that's one sign that you're done if you've connected every node. Another sign that you're done is that you can't select any more elements without creating a loop. But if you look at this, you can clearly see that we could select more elements without creating a loop. So
we can only select elements that aren't going to be causing a loop in our
exactly.
system. Okay.
So yeah, so we're going in this. So we have our two rules. So these always must apply, and then we're going to go through this order of priority of trying to include as many as possible of these elements. But once we run out of the ability to select more without creating a loop, that means that we're done. So, and we'll see that happen with this example in a moment. So the next step, 3, is to select as many as possible A-type elements. So A-type energy storage elements are capacitors for electronic systems, right? And we have a capacitor. So we still have the nodes, right? So we could draw our nodes in. We still have our voltage source. And now we're going to add the capacitor to that as well. So the capacitor comes in. And we've got one more, what we'll call branch in our normal tree. And we can now evaluate whether or not, so first of all, selecting C didn't cause a loop to happen, right? So that's a good start. Are we done? We haven't connected this node yet. And we could definitely select R2 or L without creating a loop. So we're still not done. We still have more to go. So then we go to step 4. Select as many as possible D-type elements. So we still have got our nodes. And we've still got our capacitor and our voltage source. D-type for electronic systems are the resistors, right? So R1 and R2 are resistors. If we select R1, what happens? Loop. Made a loop, and then it would be, well, we can't, I guess, is the takeaway. We can't select R1 without creating a loop, so we have to move on to the next possibility. Can we select R2 without creating a loop? Yeah, so we go ahead and do that. And now we see we've connected all the nodes, which is one thing to check. Another thing to check is if we select any other elements, any other of these edges to be in our normal tree, we would create a loop, right? So R1 would create a loop we just saw. If we selected L, it would also create a loop. But it could be the case that you reach this point and you still have the possibility of selecting more elements. If so, then select as many as possible T-type elements. In this case, we cannot select the inductor L, so we don't select it. We just leave it unselected still, and we still have our normal tree as before.
You said we couldn't select it?
We can't select it because we would create a loop, right? As many as possible T-type elements. We can't select L because if we did, this would be a loop, right?
So previously, I'm not sure if you mentioned, but you said we could have done R2 or L.
So it would not violate the loop rule if we selected L and not R2.
Yeah.
So if you did this, it wouldn't violate our loop condition, but it's in the wrong priority because we would want to do D types first.
Oh, that's the order of priority.
And that's the order of priority. So you need to use the proper order of priority. So it goes cross variable sources, A types, D types, and then T types. It's very rare that you actually get to T types and have the ability to select any of them. And in fact, we'll see in a moment that if you can select one, it means it's not an independent energy storage element. So, yeah. Cool. So, A-type elements not in, and T-type elements in the normal tree are called dependent energy storage elements. So notice, because A-types were one of the first ones we put into the normal tree, so they're usually all in the normal tree. But occasionally you'll run into situations where you can't put an A-type in the normal tree, and you'll occasionally run into situations where you have to put a T-type in the normal tree. Okay? If those happen, that means that you have dependent energy storage elements. But if you have an A-type that is in the normal tree, or a T-type that's not in the normal tree, then they're independent. The energy in these can be independently controlled. So the reason we use the term dependent or independent means that you could have, for instance, if you had two capacitors that shared the same voltage, you can't independently specify an energy for each capacitor. When you set the energy for one via the voltage, the energy for the other one is automatically linked to it. So you can't change them separately. So they're dependent on each other.
So, you said in this case, L is independent.
Independent, yep. And C is also independent because it's in the normal tree. And L is independent because it's not in the normal tree. Because they're different types of elements. So, and this is the usual situation. So most of the time, they will be independent, and the A-types will show up in the normal tree, the T-types won't, and you'll be good. But every once in a while, you run into a situation where you've got dependent energy storage elements. In order to avoid an artificial excess in state variables and construct what is called a controllable model, which is what we want to do, whenever A-types in series sharing one node or T-types in parallel sharing two nodes appear, we should first combine them to form equivalent elements in accordance with the formulas, the equivalent generalized capacitance, the equivalent generalized inductance here. And so this is a way to avoid excessive state variables. So there's the two nuances that we just introduced. First is that you can have independent and dependent energy storage elements. That's like one sort of nuance. Another nuance is that if you have A-types that show up in series or T-types that show up in parallel, we first want to combine them together. Otherwise, you're going to get an extra state variable that doesn't really tell you much. Okay, so we want to minimize that. State variables, remember, are the minimal set of variables that describe the state of the system. So that's why we do that. So when you first draw your linear graph and you see two A-types in series, like two capacitors in series, for instance, then you need to combine them first. And in fact, is it even possible to have mechanical A-types in series? Because they always have to be connected to ground, right? And so the only way they can be, it's virtually impossible to have the mechanical A-types in series. But it is possible to have mechanical T-types in parallel, which would be parallel springs. Okay. So there's that. All right. Good. So there are special names for power flow variables associated with an element, depending on whether the element is a branch or a link. So, okay. I skipped. I was going to say, I did not introduce this terminology. A lot of terms here. So, we call those elements in the normal tree its branches, and those that are not in the normal tree? Links. So the branches are the ones that we highlighted here. So branches. There's a branch. There's a branch. You know, branches show up in trees, right?
No way.
Yeah, it's a thing I've heard. I don't know a lot of biology, but I did get that far. So branches are the edges or elements, representing elements in the normal tree.
So in regards to the beginning of lecture 3.03, when we crossed out B branches for E edges, what is the difference between the branch and the edge? Or is it
Yeah, so good question. A branch, I want to just use, I want to limit its scope of definition to just elements in the normal tree, okay? An edge is, so when we looked originally at linear graphs, the two types of objects that we talked about were nodes and edges. So nodes are these guys, and this thing is an edge. So the elements in our linear graphs are all represented by edges, right? The arrows with the lines that are drawn in between the nodes. So those are edges, and we also could say parenthetically representing elements. So for example, an element might be an inductor or a spring. So when we say a branch, what we mean is very specifically, now I'm sort of narrowing it down. Previously there was this duality with the term branch, and I think it's confusing. The textbook actually uses it, and I used it too. And then when I was talking about it this morning, I realized that I wasn't a huge fan of trying to use the definition twice, so in different contexts. So this is our so these are our branches of our normal tree, right? It's like a Charlie Brown Christmas tree. It's a tree with the little branches sticking off it, and then everything else, all of the other edges or elements that didn't make it into the normal tree, we call these links because they link the branches of the normal tree. So links. So R1 is a link, and then also L is a link in this example. Cool. So branches and links. So there are special names for power flow variables associated with an element, depending on whether the element is a branch or a link, meaning whether it's in the normal tree or not in the normal tree. Primary variables are across variables on branches and through variables on links. Secondary variables are through variables on branches and across variables on links, so just the opposite, right? So let's do that for this inline example. Let's write the primary and secondary variables. So maybe we'll use this space here. So primary variables, they're going to be across variables on branches. So VS, voltage is the across variable for electronic systems, right? VC for the capacitor voltage. VR2 for the resistor R2 voltage. And then it's going to be the currents going through the links, right? So I R1 and then IL. So those are our primary variables. Any questions on the primary variables? Oh, we didn't do, yeah, we did. 1, 2, 3, 4, 5. We did them all. Okay. What about our secondary variables? We have, it's going to be the opposite, right? So through variables on branches and across variables on links. What I typically do is I trust my first. So you can do this two ways. You can either go back to the definition of secondary, do it independently of primary, and then check to make sure that you have essentially the opposite for your secondary compared to your primary. So if this is voltage, this should be current, and if this is current, this should be voltage. So whenever you see a V up there, you see a current down here. And then whenever you see a current up there, you need a voltage down here. So I tend to trust my primary and then just flip that bit over to the other one for secondary. But it's probably, best practice to do them independently and then check to make sure that they're consistent with each other. This is R1, you're right. This is a mistake. VR1. Great. Okay, so that's those are primary and secondary variables. Any questions on that or any of this? Normal tree, branches, links. Okay, cool. Let's do another one.